conservation of momentum is a very fundamental principle in physics. So before we talk about conservation of momentum, let's recall what momentum means. We know that momentum is nothing but the product of mass of an object and its velocity, and it is measured in units of kilograms meters per second. Now, conservation of momentum dictates that if there is a system of objects for any isolated system that is not interacting with anything outside, if the external force on the system is zero, that means no outside forces act on the system, then the total momentum of the system stays constant. So conservation of momentum is just another way of understanding and interpreting Newton's second law and third laws of motion. So let's look at a system of objects. Say we have two objects, which could be two cars that are colliding with each other, or any two objects that are interacting with each other. So these two objects are objects A and B. So if these two objects interact with each other, we know that if A exerts a force on B, Newton's third law dictates that B must exert an equal and opposite force on A. So if you consider the two objects as one system, these forces form an internal pair and they cancel out each other. So the net force on the system is zero, and there is no outside force acting on the system. So we know that the net force on a system from Newton's second law is the rate of change of momentum of the system. So F net equals change in momentum divided by time. So if your net force is zero, that means the right hand side must be zero, which means the change in momentum of the system must be zero. And that implies, if your change is zero, that implies the momentum of the system must stay a conserved quantity or must remain constant. So you see that the conservation of momentum principle is just an understanding derived from Newton's third law and Newton's second law. So even though the momentum of the system remains constant, the individual momentums will not remain the same. Because there is a force acting on B, B's momentum will change. And because there is a force acting on A, A's momentum will change as well. So then how does the momentum of the system remain constant? So if you think about it, if A loses momentum, that means loss in momentum of A must be equal to the gain in momentum of B. Or in other words, the change in momentum of A must be equal and opposite to the change in momentum of B, so that the net change in momentum is zero. Or we can say that there is a transfer of momentum from one object to another within the system, but the total momentum of the system stays the same. So let's look at a simulation that helps us understand what's going on when momentum transfer happens. So here are two cars that are connected to each other by some sort of a spring or something that sets an explosion and releases them. These two cars are the same mass of 1 kilogram each. So let's make a prediction before as to what will happen, what will be the outcome of this. So if an explosion set these carts into motion, will these two carts move with equal speeds or unequal speeds? Take a few seconds to think about the outcome. So let's see what happens. So notice that the two carts had the exact same speeds, but they moved in the opposite direction. Now, conservation of momentum will help us understand why. So if these are the two carts, before the explosion, the total momentum of the system is 0 because neither of them is moving. And we know that the momentum is a conserved quantity, so therefore total momentum after must also be 0. And that can only be possible if this has a momentum of, let us say, negative 10 kilogram meters per positive 10 kilogram meters per second to the right, then this should have the exact same momentum in the opposite direction, which is negative 10 kilogram meters per second, so that the total momentum still becomes 0. And since momentum is mass times velocity, if their masses are same, that means their velocities must also be the same. Okay. Now let's go back to the simulation and change something about that simulation. So let me make the blue cart heavier than the red cart, twice as much heavier. So now predict what will happen when the explosion sets them off into motion. So take a few seconds to think about what is going to happen if momentum is still a conserved quantity. Well, let's watch what happens. Did you predict right? Did you predict that the blue cart, which is heavier, moved with half the velocity of the red cart? Do you understand why? So again, the total momentum before is 0. But this cart is twice as much heavier. That means the mass is 2m, whereas here the mass is m. But we know that their momentums still have to be the same. So therefore, the velocity here must be half. So let us say the mass is 1 kilogram here and the mass is 2 kilogram. Then if this moves with 10 meters per second to the left, so negative 10 meters per second, if this momentum must be the same as this can only move with half the velocity, which is 5 meters per second. So this tells us that the heavier cart will move with a smaller velocity. Let's try a different scenario. What if we had the two masses, one is at rest and then one is going to be moving at 10 meters per second, and let's see what happens. Let's make a prediction. The red cart is at rest. The blue cart is moving with a velocity of, you want to move it to the left, so negative 10, or let's say negative 5. So the blue cart is moving with a velocity of 5 to the left and the red cart is at rest. What will happen after the blue cart goes and collides with the red cart? Let's check it. Did you get this right? So were you able to predict correctly that the blue one completely transferred all of its momentum to the red one because it came to a stop and all of its momentum went into the red one? This only happens if the two carts have identical masses. What will happen? Let's reset this and try a different scenario. What will happen if they were unequal masses? So this is 2 kilograms and this is 1 kilogram. Would it then completely transfer its momentum to the red one? Let's watch. So notice that it transferred some of its momentum, but it's still moving. But were you to apply the conservation of momentum, you would notice that the loss in momentum of the blue cart will be equal to the gain in momentum of the red cart. But it looks like the red cart had greater velocity, and that's only because it's lighter than the blue one. Okay. So momentum conservation is a universal principle and there is no exception to this law. So how do we solve problems using this concept? So let's write a general equation that will help us understand how the total momentum of a system of two objects is conserved. So let's say we have m1 and m2, which are like the two carts, moving with velocities v1i and v2i. The I stands for the initial velocity and 1 stands for the object of mass m1. So these two objects are moving with the velocities to the right at these values. If v1i is more than v2i, then you will end up with a rear end collision between M1 and M2. Boom. During collision, there are forces acting on the two masses, which means that after collision, M1 will now have to move with a different velocity because there was a force on it. So let's say V1F is its velocity and M2 moves with a different velocity, which we will call it as V2F. For convenience, we assume that all these velocities are in the same direction. They don't have to be like that. So we know conservation of momentum tells us that the total momentum before equals to the total momentum after. So if you write an expression for that, the momentum of the first object is m1v1i plus the momentum of the second object is m2v2i. So this term represents the total momentum of the system of the two objects equals m1v1f is the momentum of the first object after the collision plus m2v2f is the momentum of the second object after the collision. So this represents the total momentum after collision. So this equation is our equation that represents the conservation of momentum. You don't have to memorize this equation. It is a concept and an understanding that translates into your mathematical equation. So let's try do a